Hello, fellow students. Today we are going to work on binary trees. So we are going to refresh a bit our knowledge of theory, and we are going to complete a small exercise. I'm going to share the screen. Share my screen with you. And here you can see the exercise for today. We have a binary tree called A, and we have 4 different true or false questions. So in the first one, in A, well, basically it is asking if the tree is binary or not. So to work on this, we need to refresh our knowledge about the theory, right? So a binary tree is the one that either is empty or it has a root, which we will call R, and 2 binary subtrees. So now the most important is to realize that this is a recursive definition, right? So we are defining a concept, making a reference to that same concept. So if you know about recursive functions, this is the base case, right? This is where the recursion stops. And this is the recursive case, right? So for this tree, we will start in the root, and we need to verify that the tree is binary according to this definition. So as I said, we start in the root. Think that probably when you work with binary trees, either programming or doing any other thing, you will have a reference to the root, right? So this is the starting point for most of the algorithms that work on trees. Okay, so we are on the root. According to the definition, it is not empty, but on the other hand, it has a root, right? And then we need to check if the subtrees are binary or not, right? We need to check if the left child is binary and if the right child is also binary. So we go, for instance, to the left child, and again, it has a root, so it is not empty. So we need to check if it has 2 binary subtrees, right? In this case, we start by the left, and we verify if this left subtree is binary. So here again, it is not empty because we have a node here. So we need to check if it has a root and 2 binary subtrees. Again, it has a root. And here we need to check if there are 2 binary subtrees. So the most important trick here is that here we have empty trees, right? We have empty subtrees. So when I go to the left child, it is empty, but I mean, it's according to the definition, an empty tree, it's binary, right? So in this case, the left child is binary, the right child is binary, and as I said, okay, if it's empty, it's binary. So for this subtree, we have a root, right? And we have two binary subtrees. So it's, according to the definition, this is a binary tree. Once that we know that this child is a binary tree, we go back, right? We go back to his parent, and we already know that the left child is a binary tree. And on the right, we have again an empty subtree. So this is also binary, right? We have another root here with a binary subtree on the right and a binary subtree on the left. So again, we know that this full branch is a binary subtree. We go to its parent, and now in the root of the main tree, we need to check the right subtree, right? So again, it has a root, so we need to check the children. This one has a root, and again, it has two empty subtrees, right? So this one is binary, this one is binary, and this is a root. Okay, so we know that the left child is binary, and we are going to check the right child, right? We are going to check this one. Again, this is empty, so it's binary. The other child is also empty, so it's binary, and we have the root. So it's okay, right? As you can see, the base case, as we said before, where we stop the recursion, it's when the subtree is empty. And here we have a root and two binary subtrees. So we go back again to the parent. And in the parent, we have checked both children already. Both of them are binary. And in the parent, we have a root and two binary children. We have checked already this branch. So we go to the main root of the tree, right? In the main root, we have a root, and we have two binary subtrees, the left and the right. So again, this is binary according to the definition, right? The main root or the tree is binary according to the definition. So as I mentioned before, it's important to note that if the tree is empty, it's binary, right? It's the important part of this exercise. So in A, I would say A is binary according to the definition. Okay, in the second question, they are asking if the height of the tree is 3. Well, when we are calculating the height of a tree, the height is the path, is the length of the path that goes from the root to the more distant leaf, right? If you remember when we studied paths in graphs, we said that to measure the length, we measure the number of arcs, right? So this could be like the node b sub 0, this could be the node b sub 1, and this could be the node b sub 2, right? And this could be the first arc of the path, and this could be the second arc of the path, right? Okay, this one was false. So it's not binary, is false. And here, false. The height is 2 because it's the length. It is the length of the path from the root to the most distant leaf. Then in the next question, they are asking if A is a complete binary tree. Again, according to the definition, to be complete, a binary tree, well, we need to check these three statements. The first is that every node has two children. But okay, except the ones in the last level. The second statement is that the nodes on level h-1 with children are on the left. And the third one is that there are no single children. Okay, so we are going to draw the tree again. Right? So if we have this tree, you need to think about if we can check those three statements, right, with this tree. Well, the first thing that we see is that there is a single children here, right? A single child here. So according to this tree is not complete. But also the nodes on level h-1 with children should be on the left, right? So this node should be on the left, right? So this one is not complete. And to be complete, it should be something like this, right? We have this with this node with children on the left, and there are no single child. Should be something like this. So this one is false. And then on D, they are asking if the tree is binary and not full. So we prove that it is binary on A, and it is not full because it is missing child on the last level. So this statement is true. Right, to be full, it should be something like this. Okay, so that's all for today. Thank you very much for joining me. On the next sessions, we will talk about the different paths on 3, different ways to iterate on binary trees like pre-order, post-order, and we will make some exercise to make these concepts more clear. So stick around and see you soon. Thank you for listening to me today.